Hi, this is Maggie. In this video, we're going to start our conversation about exception handling with a discussion of preconditions and postconditions. If we want to robustly handle exceptional situations that happen during program execution, we need to be able to clearly identify when they occur. This image is figure 6.11.1 from Java Object-Oriented Problem Solving by Morelli, Wald, and Hoffman. This figure illustrates 4 types of control structure found in structured programming. What we can observe about these 4 types of control is that there is a single entry and exit point for each type of structure. In other words, we enter each structure in one location and we exit in one location. There's no chance that we leave one somewhere in the middle and never return, or that we jump into the middle of a structure from somewhere else in the program. That isn't to say that they might not be complex. We can certainly have a loop with multiple conditional statements and method calls inside. But we will eventually exit the loop and end up at the statement immediately following the loop body's closing bracket. We can use this to help us write correct code. If we look at this small example of well-structured code with comments to the right, we can see on line 2, we have a statement that k should equal 0 on line 2. After the method call on line 3, the comment states that k should equal 1. If, when running this code, k doesn't equal 0 prior to the method call, we know there's a problem with the code prior to the method call. And if k doesn't equal 1 following the method call, we know there's a problem within the method. This helps us identify the correct location to debug. We can write preconditions and postconditions to document these assertions about our program's correct state, and then use those to write defensive code that will hopefully avert or at least help us identify errors in the program. In figure 6.11.2, there are some examples of preconditions and postconditions. Let's look at those, and then we'll write some code that uses the documented preconditions and postconditions to write defensive and error-checking code. The first is quite simple. The authors are documenting an assignment statement with preconditions and postconditions. The code declares a variable k and assigns it the value 0, then assigns 5 to k. The precondition of the line that assigns 5 to k is that k is equal to 0, and the postcondition is that k is equal to 5. This very simple and straightforward example illustrates the concept. What do we know before the line or block of code, and what do we know after? We express what we know by making logical statements about the variables involved. The next is a loop. K equals 0, while k less than 100, k equals 2 times k plus 2. The precondition is that k is equal to 0, and the postcondition is the complement or logical opposite of the loop entry condition. In other words, we enter the loop because k is less than 100, and because it's a loop, we'll continue to execute the loop when k is less than 100 at the loop entry condition. But the last time the test executes, k is greater than or equal to 100, so the loop entry condition is false, and we execute the first line of code after the loop if there is one. We know k less than 100 is false for us to get past the loop. Therefore, its complement is true, k greater than or equal to 100. The last example is a factorial method, and remember that the factorial of a number is the number multiplied by the number minus 1, multiplied by the number minus 2, etc., down to 1. So 5 factorial, for example, is 5 times 4 times 3 times 2 times 1, or 120. Factorial is defined for positive integers, and it is defined for 0. 0 factorial is 1. Therefore, the precondition to this function is that n is greater than or equal to 0, because those are the only values for which this function can return a meaningful result. And the postcondition is that the function will return the factorial of the value passed. Therefore, if the precondition is met, and the value returned is not the correct factorial, then there's an error with the function. If the precondition is not met, then there's an error where the function is being called. This helps us narrow down errors, but it also helps us write code that avoids errors, or recovers from them gracefully. Now I'm going to paraphrase item 49 from the book Effective Java by Joshua Block. Item 49 is in the Methods chapter, and it is, check parameters for validity. According to Block, who is an exceptional authority on writing Java code, it is the responsibility of the method to check its parameters at the beginning of execution so it can fail with a clear outcome, rather than failing somewhere in the middle of execution when things go bad, or simply computing a garbage result that then propagates throughout the program. So our options with the factorial method are to check parameters or go ahead and calculate a factorial for a negative number and propagate the garbage result throughout the program. This could cause serious errors further down the line that would be difficult to find. The authors show us one example of how to do this, and I have that code here in Eclipse. The author's solution is to check the parameter n at the top of the method, line 7 in my version here in Eclipse, and throw an illegal argument exception with a parameter that gives some information about the exception. This sort of exception is a runtime exception, and it means there's a programming error. Now, an exception is a new flow of control, and it is not one to be used lightly. In Java, we throw exceptions only in exceptional circumstances. Throwing an exception causes control to propagate outward in the dynamic scope, or backwards through the call stack, to the nearest enclosing catch block that will catch this kind of exception. You can see that we don't have one written here. So it is handled by the Java virtual machine. That default behavior is to display the message. That's the parameter we passed when we threw and created the exception. And then display a stack trace, what methods were called to get to where the error was thrown. So what we imagine happens is that the program is run, and during testing this exception is thrown, alerting the developers to the issue with the method call. The program is then rewritten to include some input validation code before the method is invoked. So, for example, the developer could wrap a validating while loop around the input statements, or simply an if statement, as the authors do in the text, and display a message to the user in the else clause. Now, let's look at one other example. In a prior video, we created a proverb game. I'll link the video here. The proverb game creates a proverb manager object and passes to the constructor a path to a file that the proverb manager is going to use to instantiate a collection of proverb objects. The game then gets new proverbs from the proverb manager and uses them to play the game with the user. Think of the proverb manager as basically a deck of proverb cards. The proverb manager has a method called next, which returns the next proverb object in the deck. If we look at the code, we can see that the proverb manager has a field called current proverb. That is an integer index into the array list of proverb objects, and we are blithely calling get with that parameter as if there were no possibility of an index out of bounds error. A precondition on this method might be this.currentProverb is greater than or equal to 0, and this.currentProverb is less than this.proverbs.size. Meaning, this method will only return a valid result if the index is a valid index. Why are we doing no error checking here? Well, for the lower bound, we initialize the field current proverb to 0. It is a private field, and there is no code in the class anywhere that decreases the value of that variable. We have a shuffle method that resets it to 0. This is an argument for information hiding. No outside part of a program can modify the field current proverb such that it's in an invalid state. Now in next, it's incremented, so the upper bound is something that we should worry about. How do we handle that precondition? We handle that precondition by providing a method that allows the calling object, the game, to check if we are still within bounds, essentially, the hasNext method. This is part of the iterator pattern. The hasNext method returns true if there is another proverb object in the array list, if we're still within bounds. I'm going to again reference Effective Java. In the Exceptions chapter, item 69, use exceptions only for exceptional conditions, in which he suggests that a class with a state-dependent method should have a separate state testing method that can be used to determine whether the state-dependent method can be invoked. That is what the iterator pattern provides. That is an introduction to the idea of preconditions and postconditions and their value in helping us write defensive code. If you visit the Java Books website, there are self-study exercises there for writing preconditions and postconditions in section 6.11. I will include a link in the description. I will also include a link to a practice exercise that you can try that will allow you to add defensive code to the factorial.java program. Once you can do that, you're ready to move on.